When even a Nobel Prize winner in physics doubts our current understanding of the universe, everyone knows that the astronomical hour has come. However, Adam Riess is not the only one at his wits' end. The James Webb telescope is currently detecting more and more new structures in space that are in stark contradiction to the conventional cosmology. But how can it be that the existence of galactic structures that were previously considered absolutely impossible is being confirmed? What do these puzzling findings mean for future research? And have our previous theories finally had their day? Many a simple question requires a very tricky answer. For while the question of how fast the universe is expanding may sound extremely simple at first, it actually goes to the heart of a research mystery that has had experts racking their brains for many years. It's now considered certain that the universe has been continuously expanding since its birth around 13.8 billion years ago. As a result, the galaxies are also moving away from each other at a speed that is proportional to the distance that separates them. In other words, if Galaxy A is twice as far away from Earth as Galaxy B, its distance from us is also growing twice as fast. The American researcher Edwin Hubble was one of the first to recognize this correlation. In order to calculate how fast two galaxies are moving away from each other, you need to know their distance on the one hand, and on the other, you need a constant by which this distance is multiplied. And this is exactly where the so-called Hubble limit constant comes into play. And this is also where it gets extremely confusing. In fact, there has long been a major dispute among experts about how large this constant actually is. After all, previous measurements have produced completely contradictory values. In other words, the results we obtain depend on the measurement method used. One of these methods is based on the cosmic microwave background radiation. This is an almost isotropic relic from the early days of the universe, which is regarded as outstanding evidence for the Big Bang theory. If we now use the expansion rate of the universe, we obtain a value of around 67 km per second per megaparsec. To put this into perspective, 1 megaparsec corresponds to 3.26 million light-years, whereby 1 light-year corresponds to around 9.46 trillion kilometers. However, if we use so-called Cepheids to measure distances in space, or in other words, a certain type of star in which the fluctuations in brightness are strictly periodic, the expansion rate is suddenly 73 km per second per megaparsec. The universe, therefore, appears to be expanding faster in our vicinity, or in other words, up to a distance of around 3 billion light-years, than in its entirety, and this should not really be the case. In our vicinity, or in other words, up to a distance of around 3 billion light-years, than in its entirety, and this should not really be the case. This discrepancy between the different values is referred to as the Hubble tension, and so far, no researcher has been able to explain this unexpected deviation. The enigma in the sights of the James Webb telescope. Some scientists had previously hoped that the mystery surrounding the expansion rate was due to a measurement error by the Hubble Space Telescope. Adam Riess also wanted to find out whether an error had crept into the Hubble datasets. The physicist from Johns Hopkins University in Baltimore was awarded the Nobel Prize in Physics together with other researchers in 2011. The experts had discovered that the expansion of the universe is accelerating. Riess and his team used the James Webb telescope to find out the reasons behind the Hubble expansion and uncover any Hubble measurement errors. But how do you actually determine the expansion of the cosmos in detail? Well, the so-called cosmic distance ladder is used for this. Each stage of this ladder is based on the previous stage, so a potential measurement error runs through all stages. The Cepheids mentioned only proved to be reliable up to a certain point. This is because the greater the distance becomes, the more difficult it is to measure the distance accurately. The reason for this is that the light from the Cepheids mixes with the light from other stars as the distance increases, making them relatively difficult to see. Conveniently, however, Webb is 100 times more powerful than its scientific predecessor, Hubble. The Webb is 100 times more powerful than its scientific predecessor, Hubble. It allows experts to look further, and in more detail than ever before, into the remote secrets of the universe. Published in the astrophysical journal Letters, the new study then painted a rather sobering picture.
The JWST covered the entire area previously observed by Hubble and found no measurement errors. So the problem of Hubble's tension still remains, but Adam Riess has a very brief and yet profound explanation for it. It could be that we have simply misunderstood the universe. Furthermore, we must now find out whether we have overlooked something in our previous investigations, and how we can connect the beginning of the cosmos with the present. This solution calls Einstein's theory of gravity into question. Of course, the researchers around Adam Riess are not the only ones working on the confusing Hubble tension. Some scientists from the universities of Bonn and St. Andrews have also approached this mystery and found a new possible explanation. In detail, our blue home planet is located in a bubble-shaped region of space in which there is relatively little matter. The density of matter is higher around the cosmic bubble, and gravitational forces emanate from the matter, which pull the galaxies in the bubble towards the edge. As a result, they are also moving away from us faster than would actually be expected. A perfectly plausible explanation, but one that leads straight to the next research dilemma. A perfectly plausible explanation, but one that leads straight to the next research dilemma. Because the standard model does not provide for such bubbles or underdensities, they should not actually exist at all. Instead, matter should be evenly distributed in space. At its core, the standard model is based on a theory by Albert Einstein on the nature of gravity. However, it's possible that gravitational forces behave differently in reality than Einstein predicted. The scientists, therefore, referred to a modified theory of gravity presented by the Israeli physicist Mordechai Milgram in the 1980s. However, the so-called modified Newtonian dynamics has not yet achieved more than outsider status, even though it accurately predicts the existence of the corresponding bubbles. Assuming that gravity really does behave according to Milgram's ideas, all the discussions about Hubble tension would also be a thing of the past. In this context, there would actually only be one constant for the expansion of the universe, and the observed discrepancies would be due to irregularities in the distribution of matter. The future will have to show to what extent this new approach will be accepted and confirmed, but a look into the cosmic past also shows how much still needs to be understood in the future. The universe breakers 14.32. Sometimes a single value is enough to leave even the most experienced astronomers open mouths. In detail, 14.32 is the record redshift of the galaxy JADES GSZ 14-0, which means nothing other than that this gravitationally bound group of stars already existed 290 million years after the Big Bang. At the same time, the earliest known galaxy also raises some pressing questions. How could it have been so bright and massive at that time? Where did the necessary matter come from? Detected with the help of Webb's near-infrared camera NIRCam, the structure is also likely to have taken 100 million years to grow to its observed size. The bottom line is that the galactic infant contradicts practically all theoretical models and computer simulations for the very early cosmos. In fact, the galaxy is in the best of company. The 6 galaxies that the James Webb telescope had already added to the star maps at the beginning of 2023 were also much more massive than they should actually be. Although the structures already existed when the universe itself was only 500 to 700 million years old, they were already reminiscent of today's Milky Way. However, as this is simply not possible according to conventional cosmology, the galaxies earned the nickname universe breakers among experts. Instead of the unexpected baby galaxies, the researchers saw impressive objects, all of which contained more than 10 billion solar masses of stars. One of them could even have a mass of over 100 billion solar masses. The question that now needs to be answered is how this was even possible. Because even if only one of these galaxies is real, this would push our understanding of cosmology to its limits. Is how this was even possible. Because even if only one of these galaxies is real, this would push our understanding of cosmology to its limits. In order to explain the presence of the structures, the density of matter in the early cosmos would have to have been up to 5 times greater than our models suggest. Alternatively, the galaxies could have grown in a way that is completely unknown to us. But what do discoveries of this kind mean in a larger context?
Does the history of the early universe and possibly the Big Bang theory itself need to be rewritten from scratch? Well, our current understanding of galaxy evolution is as follows. First, the dark matter collapsed into giant clumps called halos. This happened within the first few 100 million years after the Big Bang. As a result, the gravity of the halos attracted normal matter, eventually forming stars and galaxies. However, this process took time. The matter would have slowly clumped together and only gradually produce larger and larger galaxies. Within this model, the galaxies discovered by Webb are therefore impossible. And in addition, our previous theories do not predict nearly as many dark matter halos in the early universe as would have been required for the formation of the large structures. And yet some experts are already finding it difficult to completely abandon the established research consensus of the past. This includes Julian Munoz from the University of Texas at Austin. Perhaps we would be better advised to interpret the data provided by Webb with a smaller scale. Perhaps we would be better advised to interpret the data provided by Webb with a certain degree of caution. He points to the following fact. If there really were 10 times more dark matter structures in the early cosmos than assumed, then there would also be 10 times more galaxies in the Webb images. However, the same would also apply to the Hubble data. But this is simply not the case. Munoz and his team counted how many galaxies Hubble had seen over a wide range of brightness. The researchers then set about the task of inserting more dark matter halos into their model of the early universe. The problem? The halos needed to match the Webb data through the information Hubble had collected into chaos. But which telescope should we trust? There is no question that Webb is significantly more powerful than its predecessor, but it only began its scientific service in 2022. The Hubble telescope, on the other hand, has been gazing into the gigantic expanses of space for almost 35 years. According to Munoz, quantity trumps quality at this point, and the Hubble data seems even more reliable at the moment. For this reason, we would currently be better off looking for other explanations for the strange early galaxies, ones that do not require us to rewrite the entire history of the development of the universe. And you now have the opportunity to help write the evolutionary history of our channel. Press the thumbs up and subscribe now, and never miss an exciting new video from us again. Thanks for watching.